Hi, my name is Christian Lilf, and I'm going to talk about our VLDB research paper, Fast Search by Classification for Index-Aware Decision Trees and Random Forests, which is a joint work of researchers from the University of Münster and the University of Copenhagen. Our research paper deals with the problem of search in large databases, which is a well-known problem in many domains where users are faced with large amounts of data and want to find interesting or rare objects of interest. Some real-world examples are, for instance, users who want to find wind turbines in satellite imagery to make an estimate about the produced energy with wind power. This example is depicted on the figure on the right, where a part of an aerial map is shown and where a user might want to find wind turbines. In the domain of astronomy, a scientist, for example, wants to find similar galaxies over astronomical data, like, for example, the well-known SDSS database. Also, reverse image search engines, like the famous Google Reverse Image Search, are an example of this search scenario. Here, a user wants to find similar images to the provided input image in the large Google image database. What all of these examples have in common is that the objects of interest are often too complex to describe in terms of query predicates. Either because the users cannot define these query predicates themselves because they are simply not trained for it, like for instance users who are not able to use SQL, or the users do not know the underlying structure of the data within the database. So the users have to treat the database as a black box. One approach to encounter this problem is to enable the users to describe the query intent by providing examples of the target objects. In the case of satellite imagery, this can be, for example, done by selecting few samples on a map, as you can see on the figure on the right. Or, in case of tabular data, by providing data samples of the object of interest. In the database community, we often speak about this approach as query by example. But within our paper, we use the term search by classification, which considers this approach more from the machine learning perspective. In the context of search by classification, a user query is defined by positive, that are instances the user wants to find, and negative examples, that are instances a user does not want to find. Based on the given data, a machine learning model is then trained to make the decision for unseen data, based on rules learned by the training data. We are going to show you how search by classification works, given an example of a user query which wants to find wind turbines in satellite imagery. In this figure, we see the individual steps of search by classification. A user query, consisting of positive and negative examples, is used to train a machine learning model. The plot represents a simplified two-dimensional feature space, in which the images are translated into and where the machine learning model is constructed. In the plot, the large red points represent the positive examples from the user query, while the large gray rectangles represent the negative examples from the user query. The smaller points and rectangles represent unseen data within the database, which is not known to the machine learning model. During training of the machine learning model, it learns how to separate the positive and the negative objects from each other based on the two given features and the training data. During inference, the learned decision boundaries of the machine learning model, indicated by the yellow areas in the plot, can be applied on unseen data of the database to check whether the instances belong to the positive or negative class. This, however, requires the machine learning model to load and scan each point of the database to check if it belongs to the search positive class or not. For large databases with billions of instances, this can easily take hours or days. We address this problem in our work with the goal to speed up the first phase of machine learning models for large datasets. Our approach fundaments on the observation that we can translate the classification models of tree-based machine learning models, like decision trees, into range queries. In the given plot, we see an exemplary classification model of a decision tree, which is shown on top of the plot. The splits of the tree correspond to orthogonal splits among the feature axes, indicated by the yellow areas of the classification model. This property enables us to translate the classification model into range queries, which can be seen as SQL statements with where clauses. Each positive leaf of the decision tree is translated into one SQL statement by traversing the tree from the root node to the leaf. Now, we can answer the initial user query by multiple range queries extracted from the classification model. But this adjustment on its own does not bring us any benefit in terms of query time. A regular database would still need to scan each point to check if it fulfills each where clause. However, if we pre-build index structures for the feature sets used by the machine learning model, we can rely solely on the index structures to answer the queries instead of scanning the database again. Thereby, we could strongly reduce the query time. In this work, we present a new search by classification framework that makes use of this technique to answer queries in large-scale databases without the requirement of scanning the whole database. Our framework is depicted in the figure on the right and is comprised of two phases. In the offline preprocessing phase, we build the required index structures in advance after the data has been transformed into meaningful feature vectors. In case of satellite image data, we would transform the image pixels into meaningful features that contain information about colors, contain shapes, and landscapes of the image patches. In the following query processing phase, the user queries are answered by our novel index-aware classifiers that we call decision branches. In this context, index-aware means that our classification model takes the pre-built index structures into account for the construction of the classification model. Thereby, our trained models can be efficiently queried without the need of scanning the entire database. We claim that the returned results of our machine learning models have the same classification performance than regular tree-based models. A challenge we had to deal with was the fact that index structures are efficient for small feature subsets with up to 6 to 10 features, but become inefficient for high-dimensional data due to the curse of dimensionality. However, in order to learn complex data, like image data, machine learning models usually require many features to achieve a good classification performance. For instance, decision trees are usually unrestricted in the number of features used for the individual splits. Therefore, if you would use decision trees directly to translate the leaves into range queries, we would end up with leaves that cover nearly all available features. Thereby, we would lose all the benefits of the index structures. Therefore, we had to come up with a new construction scheme for trees that only uses a small subset of features, but still achieves a good classification performance. A key observation during our work was that using multiple small, randomly sampled feature subsets does not hurt the classification performance. We showcase this for our decision branch models in the plot on the right. For an incoming user query, our decision branches build multiple subtrees in random feature subspaces of a small dimensionality, like in this example 2. By providing our model a multitude of these random feature subsets, our model learns a good coverage of the positive training data without missing any relevant feature. We just have to ensure that for each of the used feature subsets, an index structure is pre-built. In a second step, we could now translate the learned decision branch models into range queries. The extracted range queries now can be quickly answered by the respective index structures that were pre-built in advance without the need to scan the data. Now, we present you our underlying construction algorithm for the individual decision branches. We will not go into the details, but want to show the main characteristics of our construction algorithm. As you can see on the plot on the left, and in line 4 of our algorithmic description, we build the classification model starting from one positive instance, unlike traditional decision tree algorithms. We then expand the area in all dimensions of the feature subset until we get the optimal impurity score. In our case, it is the information gain, which is a similar approach as for classic decision trees. The expansion phase is done within the function greedy_max_gain_box in line 8. We will demonstrate the expansion phase with the example case given on the left. We begin the expansion with an area that only contains our initial point, but is already enlarged such that it covers a greater area, which makes the following expansion more likely to succeed. How the initialization of the area works in detail is described in our paper. We expand the area one dimension after another. The order is randomly chosen. In this example, we start with dimension I1. we grow the borders in both directions by including one point after another and comparing the current information gain to the overall best information gain. In the left direction, we grow the area until the next point, since this is the maximum improvement in information gain in this direction. On the right side, we grow the area until we have included 3 more points, as this represents the maximum possible information gain. This expansion is a good example to show that the expanded area will not only contain positive but also some negative samples, if that allows the area to include more of the underrepresented positive points afterwards. We repeat this procedure for the dimension I2, but now already respecting the updated boundaries in dimension I1. After all dimensions have been considered, the function returns the new bounds of the expanded area and its information gain to compare the current information gain with the scores of other areas from the remaining feature subsets. In each iteration, only the area with the best information gain is added to the final decision branch model. In our experiments, we proved 2 hypotheses. First of all, our decision branch models can compete with traditional tree-based machine learning models like decision trees and random forest in terms of classification performance. Secondly, our models require just a fraction of the query time of scan-based approaches because of the utilized index structures. In our experiments on the classification performance on 6 well-known benchmark datasets, we show that our individual decision branches have a similar F1 score than decision trees. In the comparison of the ensemble methods, our decision branch ensemble could even outperform the traditional random forest while being almost on the same level than the extra trees. In the experiments on the query performance, we could also demonstrate the expected outcome. On a large-scale case study on more than 1 billion aerial image patches, we could show that our individual decision branches could answer the query about 700 times faster than the scan-based approach, while keeping the same classification performance in terms of F1 score. For the ensemble models, we could achieve an improvement in speed about 200 times compared to the scan-based competitors. Note that these differences will even increase for larger datasets. All in all, we could present you our new search by classification framework that enables fast and accurate query execution for large-scale databases. We think that our approach will pave the way for new index-aware machine learning models that can be used for search engines in data-intensive domains. Potential future research directions can focus on reducing the storage overhead that comes with the pre-built index structures by, for instance, using compressed or learnable index structures. Also, more research can be conducted on how to handle incremental updates in the index structures. Promising solutions can be implemented with LSM trees. For more insights, we refer to our corresponding paper, which you can find following the given QR code. There you can also find a link to our publicly available codebase. Furthermore, we invite you to use our first prototypical search engine named RapidEarth on web.rapid.earth, which adapts our presented search by classification framework for a satellite imagery search engine of Denmark. Thank you for listening.